and hopefully started. All right, it's a pleasure to introduce the next speaker, Sergej Monavari from the University of Utrecht, telling us about stable pair invariants of local Calabi-Yau fourfolds.
So thank you very much. So let me thank all the organizers for inviting me to your nice conference. So today we'll report on some joint work with Yalong Cao and Martin Cole. I want to essentially in this talk, I want to give a sort of gentle introduction to this sort of new topic, this Donaldson-Thomas theory for Calabi-Yau fourfolds, which is one dimension higher than you would classically expect. But then I will also to give some concrete examples of which kind of computation you can really do and report some kind of state of the art in the field. So, okay, great, there's no lag. So roughly speaking, so in this talk, it is roughly divided in two parts. So since I don't expect many people to be acquainted with the, let's say, the language and the framework that have been developed to answer the question, how do we count sheaves on Calabi-Yau fourfolds? The first part will be a little bit more foundational, in which I will address this question. While in the second part, I will focus more on how we can actually use shift theoretic invariants, in my case, table pair invariants, to give a shift theoretic interpretation of curve counting invariants, which are Gromov-Witten invariants and Kopakomarov type invariants, which I guess that would relate to BPS numbers and then I guess would be of interest to the audience, the diverse audience of this conference. In particular, then I will focus on many examples and techniques that we developed to actually compute this kind of invariants, and in particular, we'll focus on local surfaces. So fourfolds that are obtained by starting with a surface, algebraic surface, complex surface, and then we take two line bundles over that. Let me also stress that in here there are, let's say, many foundations that one can use to introduce Donaldson-Thomas theory of fourfolds. Some of them, so the first one was developed by Cao and Long, and then along that path, using derived algebraic geometry, the problem was addressed by Borisov and Joyce. However, I will use a language that I prefer because it's more algebraic, that has been developed by Owen Thomas last September, which also means that if I were to give this talk last year, as it was supposed to, the first half would have been completely different. So there is some good in it. Let me really start from some motivation. So why would different people in different areas would be interested in studying Donaldson-Thomas theory for Calabi-Yau fourfolds? So already Donaldson and Thomas, so from the perspective of mathematical physics, so were led by gauge theoretic consideration. They were wondering, okay, can we extend that to 4 complex dimensions? And that was indeed the path that was initially taken by Cao and Long to really define Donaldson-Thomas invariants for Calabi-Yau fourfolds. Which, as I was saying, then was expanded by Borisov and Joyce. However, from the more enumerative point of view, in a sense, it's from the curve counting point of view, it's already natural to consider curve counting invariants because Gromov-Witten theory, it's well defined in any dimension. So this was done by Clement Pandaripande, which also described how to relate Gromov-Witten invariants with Kopakomarov type invariants for Calabi-Yau fourfolds. But then it had also been recently addressed by Bussobrin and Van Gaarder in the context of the log local principle, something I'm not expert of, but I guess we have all the experts in here. Then indeed, if you want to switch from more mathematics to more physics, to theoretical physics, if you like topological string theory, a la Nekrasov, then you can really use Donaldson-Thomas theory, both for threefold, but also for fourfolds with this new setting, to describe some matrix quantum mechanical models. So not fully acquainted with the language, but there are a lot of connections there. And just as a final bonus, so if you do like combinatorics, so you can either use really combinatorics to solve and reformulate all of these geometric problems, or you can use the geometry to give some interpretation of some problems that were raised and basically not solved already starting from McMahon. So let me start the first part, really introducing what is the setup in which we can study Donaldson-Thomas theory. I will be a bit more general here, but don't worry because in a couple of slides, all varieties will be Calabi-Yau fourfolds, so we don't have to worry too much. So the setup that we are considering is the following. So we start with a smooth projective variety. Everything will be over the complex numbers with a chosen polarization. So we choose a very ample divisor over it. Which are the moduli spaces that we are interested in? So if you want to count sheaves, well, there are the following spaces where we parameterize torsion-free sheaves on your variety that are stable, so Giesecke stable with respect to the polarization. And then to fix some finiteness condition, then we want to fix their chain character. As in more physical terms, it means that we are fixing some brane charges. So this assumption, just to make our life simpler, we just require that stable is the same as semi-stable, just to rule out some technical problems, but I guess that the theory will be in the future nicely developed also in a more general setting. So the first thing that you have to do if you want to study sheaves and count sheaves and moduli spaces of sheaves, you have to study its obstruction theory. So if you know how to control how the sheaves are deforming inside your variety, then you have some hope to start studying the moduli space and get some counting theories out of that. Already here, let me restrict to X the final Calabi-Yau, but again, it's not important. Everything will be Calabi-Yau since the next slide. And here, we already know it's classically know how to study the deformation theory of such sheaves. In fact, you know that to control that, you just need some homological algebra. In particular, that means that if you want to study the deformations of such sheaves, you know that they are controlled, parameterized by the first trace-free X group, is 0 just for the trace-free. Then the obstructions to the deformation are controlled by the X2, so the second one. And then the larger the dimension of your variety, then the nastier the higher obstruction spaces will be. And then they will make much more difficult to study and perform some countings on your variety. So what happens is that classically people have been studying such problems in dimension up to 3, particularly for surfaces and for trefolds, not only Calabi-Yau, but although more generally. And it is that so the moduli space is not always smooth, so our life would be too easy if that was always the case. But in dimension 3, then we would not have such higher obstructions. And then the deformation theory would just be controlled essentially by two pieces, by the deformation, this X1, and by the obstruction, this X2. And as soon as we have such a nice setting, roughly speaking, we can use the language and the machinery of Berenfantecchi and Litiano of perfect obstruction theory to produce some virtual fundamental classes. And as soon as you have virtual fundamental classes, you know how to define invariants because you just have to integrate some classes against this class. So the first natural question that arises is, okay, so say that we want to perform some computation on fourfolds. How do we control the higher obstruction? So this piece here. And the answer is, in general, you cannot. So you have to just give up and not think about it. But you can say something if you restrict yourself to Calabi-Yau fourfolds. That's why it gets very important. So just for this part, let me just, as a bit of notation, as a projective Calabi-Yau fourfold, I will mean projective fourfold such that canonical bundle is trivial, and then we just require some standard vanishing in cohomology. I guess that if you open 10 different papers, there will be 10 different notation and definition for Calabi-Yau. So it is the main feature, actually the only feature that we can extract and exploit for Calabi-Yau fourfolds in order to study the deformation theory. The point is that we can use Serre duality, and thanks to Serre duality, we have here, of course, we are doing it pointwise for every sheaf. We have that the X1, which controls the deformations of the object, is dual to the X3, which controls the higher obstructions, which was this extra piece that we have to understand how to control. And then the second feature is that the X2, which controls the obstruction space, is self-dual, again, thanks to Serre duality. So the moral of this is that we can kind of relate the third piece to the first one, and in particular, the obstruction space is endowed with a quadratic pairing. So we really need Serre duality here, so we really need the Calabi-Yau condition. So now I want to explain how one can use this unique feature, this quadratic pairing, to construct some virtual classes, at least roughly speaking. However, before doing that, let me review a little how the classical construction goes of constructing virtual fundamental classes. So I'm gonna review a little how the language of Berenfantecchi works. It's much more general than what is written in here, but this is what I like to call the toy model, because I think it's nice and really explains how the picture goes. So if you're not aware of this model, so how does it work? So it's very simple. So you start with a smooth ambient space, A, and then you take a vector bundle over it, E, so any vector bundle, and say that the vector bundle has a section, S. So what happens is that the section will naturally cut sub-objects, so there's a variety, a sub-scheme of your smooth ambient space, being it projective or not. The point is that usually the section will not be regular. So if you have some equation defining your Z, they will not be independent, which means that then the dimension of Z, which will not be the one you would expect. So it will not be the dimension of A minus the rank of the vector bundle. If that were the case, what would happen? It would happen that, so forget the virtual here, you would have a fundamental class in homology, and you would know how it pushes on the smooth ambient space. It would just be given by the Euler class of the bundle, and everything would be really nice. So the feature of this toy model of Berenfantecchi is that in the general case, even if it is not transverse, you have something called a perfect obstruction theory, which gives rise to a virtual fundamental class, which behaves as the section was cutting regularly the subscheme. So the virtual fundamental class always pushes to the smooth ambient space with the Euler class of the bundle. Let me just say what is this perfect obstruction theory. This is a map in the derived category of Z, where the target here is the truncated cotangent complex, which is controlling, in a sense, the deformation theory of your space, Z. The source instead is a perfect complex of two terms of locally free shifts. In this very nice example, in the first term here in degree 0, we have the tangent space. And then here in the second, in degree -1, we have the dual of the vector bundle. And of course, this generalizes. So this is just a toy model, but in general, there is a notion of perfect obstruction theory. There are some axioms that you have to check, but you can produce such classes. The main feature here, which is really important, is that this complex is really given by two terms. So morally speaking, these two terms should correspond in a sense to the deformations and to the obstruction. So having this perfect obstruction theory allows you to control these two kind of pieces. That's why, let me scroll back. That's why before in here up to dimension 3, we could use that machinery to produce visual fundamental classes. So let me upgrade now. Well, not really upgrade. Let me change the setting now to, at least roughly speaking, explain how one should adapt this sort of toy model to include Calabi-Yau fourfolds into this picture. It is the following. So let me guide you through all of these construction. Here I'm going to refer to the Thomas construction because it's kind of a toy model that arises out of their work. Again, you start with something simple in a sense. Again, you start with a smooth ambient space, A, and then you take a vector bundle over it. So in a sense, the most naive thing that you can think about. However, now we require some extra structure, some extra data that we want to attach to this vector bundle. In fact, we want it to have a perfect quadratic pairing that in our case, then it's going to be played in a sense from the third duality. Then we take, what do we take? Then we take a section of our vector bundle, but again, we want some extra structure. We want something stronger. We want the section to be isotropic with respect to this quadratic pairing. As before, it turns out that you're going to have a subscheme here, Z. Of course, if you forget about this red extra structure, if you forget about this red extra structure, you still can see that as a sort of Berenfantecchi toy model, you would get a Berenfantecchi virtual class. The point is that often, at least in this setting for Calabi-Yau fourfolds, it will not be the correct one. So what is the correct class that comes in here? The idea is that before we had a two-term complex mapping to the truncated cotangent complex. Here instead we have something slightly different. We still have an obstruction theory, but the obstruction is not perfect anymore because now it's given by 3 terms. So let's see what are the terms here. Again, as before, in degree 0 we have our tangent space, so there's the restriction of the 1 forms. Then in degree -1 we have the dual of the vector bundle, which is cutting out our subscheme Z. But the important piece here is that we add a piece in -2, which is the duals of the 1 forms. And now you should really recognize from here the situation that we depicted before for Calabi-Yau fourfolds, because you already see that if, morally speaking, these pieces are in a sense controlling the obstruction spaces, you see that what's sitting here is dual to the last piece, while the piece sitting in the middle is self-dual. So this is really the toy model that we would like to use to produce classes. Of course, autonomous construction is very technical, requires a lot of intersection theory and deformation theory, but their output is something very concrete because it's a virtual fundamental class, similarly to Bellin-Fantecchi construction. So here I'm writing homology, but of course, all of this construction is algebraic, so you should really see it in Chow. Then, of course, you can map it to cohomology or homology. The only point, the tricky point here is that if you want to perform the construction, at least algebraically, you really need to invert 2 here. Otherwise, it will not work. This is, in a sense, something deep. The moral is that the guiding principle for fourfolds will be, in every slide, more or less, we will either be forced to invert 2 or extract square roots, and this will be the main feature about fourfolds that I'm going to try to explain. The second feature, which is very nice in this toy model, is that it's really explicit in a sense. This virtual fundamental class, so no matter how S is behaving, we know we can push it on the smooth ambient space, and we know on the smooth ambient space how it is. And it's again given by a characteristic class, just that this characteristic class is not as simple as before. It's not just the Euler class of your vector bundle, but it is the, it is the square root Euler class, which is a characteristic class that was defined by editing Graham for vector bundles with quadratic pairings. I'm going to explain a little bit more than how to work with these square root Euler classes. Do you have any questions so far? Okay, so if not, let me go on with this first part. And here I just described a toy model, which often it's not enough, but gives all the information and relevant pictures to understand how it goes. But let me just say which is the more general recipe that you can use to produce classes and virtual structures for fourfolds.
Sorry, I have a quick question actually, just very quick. Can you just repeat the reason why in this toy model the existence of this virtual fundamental class holds?
White holes?
Yeah.
I mean, that's of course part of all of their construction, but
okay,
the idea is the following. The idea is that you see here you have this 3-term complex, which behaves nicely because you have that this piece is kind of dual to this other, and this piece is self-dual. The idea is that you're using the isotropicity of your section to, morally speaking, split in half this complex. So keeping this part and try to extract half information from this bundle using the isotropicity. And this extracting half will give you a complex which is just given by 2 terms. So you can go and rely on Bellin-Fantecchi construction, of course, with many adaptation. But that extracting a square root will introduce, that extracting half will introduce all the square rooting that we are going to produce. So this is why you need the isotropicity and this quadratic pairing to go over it.
Okay, thank you.
I hope that answers.
Yeah, thanks.
So let me explain briefly, modulo some very technical assumptions which involve a bit of derived algebraic geometry. Let me explain how you should think of globalizing this construction. It is the following. So again, you start with a space M. Then you want unobstruction theory. And you want, the point is that you don't want, it's not perfect anymore. So E is not anymore a complex of perfect amplitude -1, 0, but it's now -2, 0. So it's given by 3 terms. And we want it, this complex E, to be self-dual. And this self-duality has to be induced by a quadratic pairing that you can put on the determinant line bundle. So before, I mean, it was easier because you just had to put it on the vector bundle, but this is more general. However, this is still not enough because essentially the important piece here is that usually, for example, when dealing with, in our case, with surduality, this quadratic pairing is quite canonical. I mean, you know how to put it, you know why it should exist. What is not canonical is the choice of an orientation. So what does that mean? It means that an orientation is a square root. Again, we need square roots kind of everywhere here of this quadratic pairing. It means that it's an isomorphism of the determinant bundle with the structure shift, such that one square, you recover something that was canonical before, this quadratic pairing. Orientation issues is one of the, let's say, difficult part of the theory, not something that I dealt with myself, but we are lucky because essentially Dominic Joyce, with his long list of students and postdocs, they produce orientations for modular spaces of Corin shifts on fourfolds in many cases, both projective cases and quasi-projective cases. But it's an important feature of the theory. Let me also say that if orientation exists, the form has a two torsor over your space, which means that globally, if you have one, you have at least two, because you can just change the sign of the orientation. And this is pretty much important. I will come on it later. Let me finish these first, let's say, foundational parts, just saying a bit how you should think of this square root Euler class. So what does that mean, and how you compute it? Because in the end, if you want to perform any kind of checks or computation and not just in the Platonic world, then you really need to know how to teach a computer how to compute these square root Euler classes. It is that in general, say that our E, it's our vector bundle with its quadratic pairing, say that it admits a maximal isotropic subbundle. This is not usually the case. It's far from being the case. If it does, so the inclusion of this isotropic subbundle induces the following short exact sequence where the co-kernel is just given by the dual of lambda. And how do you define the square root Euler class of E? Either define or how you prove that it's actually this. It's just up to a sign, which you have to introduce because you could change lambda with its dual, for example. It's just the Euler class of lambda. So this sign, of course, you need to make some choices to define that. And that will also depend on the orientation if you want to fix precisely the sign. But this really shows why it's called a square root Euler class, because if you happens to have this short exact sequence, and if you just square this square root Euler class, again, up to a sign, which you can control now, you recover the Euler class of it. So it's really a square root. So here I wrote Chow really because I want to stress the fact that it's algebraic, but you can think of cohomology here. Already in Chow, the point is here, you see that here, again, I'm asking to invert 2, which is in a sense something strong. Then you should wonder, why are we asking that? You're just defining the square root Euler class as a characteristic class that definitely lives on the cohomology. You don't need that. The point is that in general, you will not have globally this maximal isotropic subbundle. So the idea is that you don't have it, but you have if you replace your space with a suitable cover. So you replace it with a suitable cover. On the cover, you have the maximal isotropic subbundle. You define the square root Euler class, and then you push through the covering. In pushing through the covering, you find out yourself that you are forced to invert a power of 2. So that's essentially why the inverted 2 comes in all of the story.
Sorry, excuse me. Yeah, but how can you choose your cover? Like, is there like a canonical way to choose your cover?
Yeah, there's a canonical way. So I'm not acquainted with the construction, but basically you have the space where on every point you choose, on every point you take the fiber of your vector bundle, on the fiber of the vector bundle just a vector space with its quadratic pairing. You find there the maximal isotropic subbundle, and then it turns out that this actually is a cover. I wouldn't know here on the spot to say which is the degree of the covering, but you can always produce that. So, but it's explicitly described in Ottoma's paper.
Appreciate.
But I guess that already editing Graham described that in order to show that you can construct always these square root order classes.
Appreciate.
Yeah, so this was regarding the more foundational part. In the end, I just described a language that is gonna be used in order to define invariants. However, actually what happened is that what I'm gonna describe in the second part is really work that was done before having this language. Because of course, then you conjecture some techniques and you develop some technology in order to perform computation and compute invariants with many examples. Then I guess then just led to the formalization with this new language. But since we have it, I think it's nicer to just reverse the logic order and see how it formally goes. So let me switch to something more enumerative, something which I like the most. This is a little recap of the curve counting side of the story, which I guess ultimately relates to the interests of this conference. Here, of course, everything that I wrote virtual here is the Beren-Fantecchi virtual structure. Here, we don't need all of this structure and technology that I introduced before. So what is the story here? Here, let me already focus on X as a Calabi-Yau fourfold. Now, I will always take X to be a Calabi-Yau fourfold. How do you define curve counting invariants? So we have a more or less canonical theory to do that. It's Gromov-Witten theory. So what happens is that you take moduli space of stable maps. You want to fix some genera. You want to fix some number n. The point is that for Calabi-Yau fourfolds, it's peculiar because if the genus is greater than 2, then all the Gromov-Witten invariants, they just vanish because of dimensional argument, because this virtual class would just have negative virtual dimension. So the only interesting cases are for genus 0, so counting rational curves, where virtual dimension is 1, so you put one point insertion usually, well, not just point, you put some insertion, where gamma is some homology class on X. And then you have for genus 1, so roughly speaking, counting elliptic curves. Here the virtual dimension is 0, so you're really counting the degree of this virtual cycle. Let me stress here that it's really important if you do Gromov-Witten theory that here, whatever you're getting as an answer are rational numbers. Whether you get rational numbers is essentially because these moduli spaces, they're not representable. They're given by some stacks, some orbifolds if you want. And so whatever you're counting by weighting the automorphisms of the stuff you're counting. So already for threefold, so in lower dimension, as it was also already described today, one feature in order to study Gromov-Witten invariants is to package all of them into a generating series and ask, okay, can I formulate that in another way such that I can extract some integer invariants that then are completely controlling my rational invariants that are the Gromov-Witten ones. This was done for threefolds. And it was also done for fourfolds by Clement Pandaripande in 2008. So here I'm displaying the formula for genus 0, but there is an analogous formula also for genus 1, where they wrote a multiple cover type formula, you see it here, introducing these invariants that I'm going to call GV invariants that are conjecturally integer. And of course, there is a similar story also for genus 1 with meeting invariants that it's just longer to display. So this is something very deep. And also the integrality conjecture is, let me say that it had been proven by Yonel and Parker using symplectic methods recently. And if I'm not wrong, also in some easier settings, Lusobrin and Van Garel, they proved, for example, for local surfaces using all of their curve counting theories, they proved in some cases the integrality, again, just for genus 0, if I'm not wrong. So once that we have this correspondence between Gromov-Witten and Kopakomarov alpha type invariants, The natural question is, that was already raised by Clem and Pandaripandi, is, can we give a shift-theoretic interpretation of these invariants? At the time, they could not, because essentially, Thomas model, or if you want, Borisov-Joyce construction, or all these tools from derived algebraic geometry, they were not available. So the language was not there, because you cannot just extend Donaldson-Thomas theory in any dimension as Chromo-Witten. So what I'm going to describe now on is how you can introduce some interesting shift-theoretic invariants that will give shift-theoretic interpretation of these numbers. And if you may ask, why do you want to do that? Well, it is also a way to introduce new techniques that will allow you not only to interpret these invariants, but also to really compute them from a different point of view. So let me say here, so there are essentially two ways that were introduced by Tsao, Malik, and Toda to give a shift-theoretic interpretation of these GV invariants for fourfolds, Calabi-Yau fourfolds. One is with stable shifts, and one is with stable pairs, which are not these stable pairs that Tony, you introduced before, just overlap of notation. I prefer the stable pair side, so this is the one I'm going to explain and talk about. Let me say in general what are these stable pairs, what is this moduli space. This moduli space was introduced by Pandaripandi and Thomas, 2009, as a mean to give a more geometric interpretation of the MNOP conjecture, which related for threefolds, Gromov-Witten invariants and Donaldson-Thomas invariants. So there's a nice story behind this. In general, how does this, what is this moduli space? This moduli space is the following. So you start again with a smooth projective variety, whatever dimension now. You fix a non-zero curve class, beta, class in homology, and then you just fix some integer n. The moduli space parameterizes the following. Parameterizes shifts on X with a section S. However, you want to see this not as a pair shift with a section, but as a complex in the derived category. I will not need it now, but the point is that if you want to correctly understand what is the deformation theory of these objects, you have to see those as objects in the derived category. Which requirements are we putting on these objects? So F, we want it to be a pure one-dimensional sheaf. And the one-dimensional support, we want it to be in the class beta that we fixed. And for some finiteness condition, we also fix the holomorphic Euler characteristic. So it may seem, let's say, weird moduli space, but let me give really what I like to be the prototype of these pairs. It's just essentially, if you take any curve C, curve class beta, then you may think of such surjections. So it's surjective, so it's even zero-dimensional co-kernel, and then you can also twist it by some divisor on the curve. So this is really the prototype that you should keep in mind. So what happens is that these moduli spaces, again, had been studied a lot, especially in dimension 2 and 3, because they give a lot of very nice geometric interpretation of many problems in enumerative geometry. Dimension 2 and 3, again, sometimes it's smooth and sometimes it is not, but still, you just have two pieces controlling the deformation theory. So you can use Behrens-Fantacchi construction. Dimension 4, you have to require Calabi-Yau condition. Again, these moduli spaces do not fall precisely into the family of spaces I described in the beginning, but are very close to them, which still means that you can apply Thomas construction there. So everything that I said in the first part applies here. So we get those kind of virtual structures. Let me say here that usually what you would expect for moduli spaces of shifts over Calabi-Yau threefolds is that the virtual dimension would be 0, and then all of your invariants would naturally have some motivic behavior, let's say, that led to all of the refinements that I've been studying the last 15 years. Here instead, even if we require Calabi-Yau, it's not true that the virtual dimension is 0. In fact, the virtual dimension is n, which means that in general, you have to put some insertions to make sense of the geometry to get numbers. So it's in a sense less canonical and for sure won't be motivic. So there are many choices of insertions that you can think of. Let me just describe one here, which is the one that we used in our project, but in the end I will say something more general as well. The invariants that you want to put here are called primary insertions. So what are these insertions? So you start with gamma, which is a cohomology class on X. Then you pull it back to the product of X with your moduli space of stable pairs. Then you cap it with the tertiary character of the universal stable pair, so the universal object there. And then you push it back to your moduli space. So you have naturally produced some cohomology class on your space. What do you want to do that? Well, this is essentially what corresponds for stable pairs to the, let's say, evaluation for Gromov width. So that's how you would correspond invariants that really come from X. So here now we have all the language set up because we have the moduli space, and then we have the invariants, and then we have the virtual fundamental classes. So I just need to tell you how these invariants now are giving a shift theoretic interpretation of GV invariants. And the story goes like follows. So I'm going to refer here as the Kopakumar-Vafa stable pair conjectures. Of course, there are analogous conjectures also if you want to see these as invariants coming from stable shifts, not from stable pairs. The conjecture were given by a series of, in a series of papers by Tsao, Malik, and Toda. There are essentially two conjectures, one for genus 0 and one for genus 1. Let me just remind you as a notation, these N1 beta and 0 beta, oops, are the GV invariants that were introduced by Clem and Pandaripande, and that relates to the Gromov-Witten invariants. The first conjecture is about the N equals 0 and the G equal 1 GV invariants. You see here there are no gammas because both moduli spaces, they have virtual dimensions 0, so you don't need insertions to define invariants. And the conjecture is saying that if you plug into a generating series all your stable pair invariants for N equals 0, N is the holomorphic Euler characteristic of your sheaf F, then you get just a product of, you just get a product of shifted McMahon functions raised to the power of these GV invariants. What I find much more interesting is the second conjecture. Second conjecture, here I wrote for simplicity for all the same gammas, but if you open the papers of Tsao, Malik, and Toda, there are more, let's say, general conjectures here. Here it relates for a general N, so as high as you want, stable pair invariants. So of course you need to put some insertions. It relates to, again, what? To genus 0 GV invariants and to N equals 0 stable pair invariants, which in turn you can again relate to GV invariants. So for the higher ones, you relate both to the genus 0 and to the genus 1. The nice thing here is that for this second conjecture, already Tsao and Toda, they gave an interpretation of this as a wall crossing of D0, D2, D8 bound states. Of course, they cannot prove it, but what I understand, again, I hope I'm not mistaken from conversations with Arkady Boyko, is that you should be able to use this new machinery of wall crossing that Dominic Joyce is developing to say something on these kind of formulas and wall crossing type of formulas. So, but he's more the expert. To me, that's really some very difficult new machinery. Let me also say that something that is very interesting in here about these formulas is that one cannot catch it immediately by seeing at these formulas, but you see that all of these formulas, they have many of these N and beta at the same time. The idea is that I told you in the beginning that to define these invariants, you need a choice of orientation of your moduli space, whatever that means. And I also said that if you have orientation, you always have at least two globally. So changing orientations means that you have to change the sign. If you change the sign of the virtual class, then you also change the sign of the invariants. And that's very important because if you're interested in one of these invariants, you can just say, okay, let's keep it just up to a sign. But if you want to consider such kind of wall crossing, it's really important that these orientation, they have to be compatible with each other in some sense. Again, also regarding the orientations, what I learned with discussion with Arkady is that the wall crossing should also tell you how the orientation should be compatible with each other. So you should be able to wall cross them in some sort of sense. But this is a very important feature of the theory. This also led to many problems in the beginning, because in the beginning we had no idea how to relate these invariants each other, and then not even having them well defined just up to a global sign made everything very, very difficult to study. So these were conjectures, and of course, if you have conjectures and you want to convince people that this conjecture should actually hold, then you should produce some evidence. Evidences were essentially given by two groups of people. One was by Zhao Malik and Toda, and Yalong Zhao himself in their series of papers. They produced many examples in many different kind of geometries. Let me just report briefly which kind of geometries are these. So these kind of geometries are the following. So they take either general sextic, or they take some elliptic fibrations, or some local Fanon varieties. The problems with their evidences is that it's nice evidence, but usually it's very low evidence, in the sense that n, it's very limited, always either 0 or 1. And then also the class, it's very low usually. It's either irreducible classes or some easy classes or low multiples of something you can just control. So let me just scroll back. And then, of course, if you take a class which is irreducible, you just realize immediately that it's very difficult to check such kind of statements where you really want to split as much as you can your class. So this really motivated us to pursue the hunt for new evidences, and in particular, not just some evidences, but to develop some techniques that could be applied more generally, and then some techniques that could lead us to perform as many computations as possible. Of course, in some geometries that I'm going to explain. In fact, whatever I'm going to explain, which is the heart of the work, at least of this work with Yalong Zhao and Martin Koh, is can be applied for n as high as possible, and also of beta, which can be as high degree as possible, and also in particular non-irreducible. That's the main difference with their work. Let me say here that, of course, we had been lazy, so we just selected some varieties that we wanted to study. Otherwise, you just spend years just producing new evidences. The kind of examples we looked at were, so we took some the Petzl surfaces, or let's say weak the Petzl surfaces. So in our case, we just took them also to be toric. It's not necessary. It helps our life, and we were already studying toric varieties, but it's not necessary. And then we take some, so here F1, F2 are just Hirzebruch surfaces. And then we take the total space of two line bundles. So we get Calabi-Yau if you require something extra. The other nice set of examples are if you take just some Fanon threefold, and then you take the canonical bundle over it. So let me tell you something more about these local surfaces. So let's try to get into the point of which kind of techniques we developed. So again, local surface will mean for us today that we start with a surface S, then we take two line bundles such that the retensor product is the canonical bundle. This will mean that X will be a local Calabi-Yau fourfold, so will mean that it's Calabi-Yau, but it's non-compact. This is how I like to think of these local surfaces. We have two compact directions given by S and two non-compact directions given by the line bundles. The whole point here is that it's very nice. They're easy to construct, and you relate to the geometry of complex surfaces, which is better than, easier to study than fourfolds. The point is that if X is non-compact, usually also the modular space will be non-compact. And that's very bad, because if it is non-compact, there's no way to produce numbers, because you cannot perform intersection theory in the usual sense. There are some ways in which you can get around this. However, we are lucky because sometimes it is compact, and that's very nice. As an example, if you take P2 or you take P1 times P1, and you take these two choices of line bundles, for example, for P2, you essentially take the dual of line bundles corresponding to a line and the line bundles corresponding to a quadric, you get a moduli space which is compact for all beta and for all n. This is very nice. Again, this is very roughly speaking. Why do you expect compactness? Is because the negativity of this normal bundle forces your sheaves to live inside the zero section, set theoretically. Scheme theoretically, they can thicken out, but they cannot thicken out too much, so still compact. And the co-kernel, the zero-dimensional co-kernel, has to be supported on the curve, so it's also bounded in a sense. This is very different from Donaldson-Thomas theory, where you can just have curves supported here, and then points that roam around and they just go to infinity, and so this is contradicting compactness. So having in mind these two very nice examples where when it is always compact, we try to push it as far as possible. Not as far as possible because we wanted some finite number of cases, but we just asked, okay, let's suppose that we want to find when the moduli space is compact so that we can perform intersection theory. So this is important. These two are also important because otherwise there would be something wrong going on with the theory, but let me not explain how they're used. These two conditions instead are not that important. So it's not really important to have minimal and toric, just that we wanted to have some zoo of varieties that we could more or less control. Turns out that if you require all of these assumptions, there are 6 possible cases. 2 of them are the one of before, and the others are another choice of P1 times P1 and some Hirzebruch surfaces. Let me say that looking for these Hirzebruch surfaces was really motivated by the I was motivated to do that after a talk in Trieste of Andrea Brini, where he was doing the GV side of the story for this kind of surfaces. The interesting part here is that while for the first 2 cases, it's always compact the moduli space, this is not the case for the other 4. For the other 4, it is compact just for some choices of beta and n. And this is in a sense a very interesting feature because all of this wall crossing is in a sense moving around, changing the beta, changing the n, and then you have the relation with the GV side. And sometimes the corresponding moduli space on the curve counting theories is compact while our is not. So this led to many, let's say, interesting studying on the geometry of this space. Let me just explain you really briefly what I was saying before, why you really expect compactness here. The compactness is really given by the fact that if you require your curve class to live in here, and you have a sort of negativity of the vector bundle, or almost negativity in a sense, let me not explain really what that means, then you can force your sheaves to live in a thickening of the zero section, and the thickening is given. So this D is determined by beta and n. And the co-kernel, again, has to live inside here. So that's why we get compactness. We get compactness, we get something that relates to surfaces, but again, usually this D is not 1. So you don't just have stuff which is supported on the surface. So what we did is that for the first technique that we wanted to develop, we restricted furthermore ourselves, and we said, okay, so let's suppose now that not only everything is set theoretically supported on the zero section, but also scheme theoretically. So say that the moduli space of sheaves on the fourfold is isomorphic to the one on the surface itself. This is restrictive, but still has many cases into this family. And in order to fully classify when this happens, we adapted an argument of Choi, Katz, and Clem that was used for threefolds, just adapted it 1 dimension higher. The nice feature here is that now you have a moduli space, which you can see as a moduli space of sheaves on a Calabi-Yau fourfold, or you can see as a moduli space of sheaves on a surface. And I said before that if you see that as a moduli space of sheaves on fourfolds, you have a virtual fundamental class a la Thomas. But then if you see that as a moduli space of sheaves on a surface, you have a way to construct a virtual fundamental class, which was done by Colin Thomas using relative Hilbert schemes, using Berenfantaki construction. So the first thing that you should ask is, okay, so say now that I want to relate the two of them. So how do I compare them? So we did that. And the comparison is just given by a sign, which really relates to this choice of global orientation that is used to make the compatibility for the wall crossing conjectures. And then the second piece is just a characteristic class. So let me not explain that, but I mean, it's very explicit. It is that once you have this translation from fourfold to surfaces, your life gets easier because you can compute invariants by pushing everything, first reducing everything to the surface. Then the surface, what I was saying, Cole and Thomas, they proved that this is isomorphic to a relative Hilbert scheme of points. We don't care about that now. We just care that this embeds into a product of a Hilbert scheme of points, which is smooth, so very nice, and a Hilbert scheme of divisors. This Hilbert scheme of divisors, usually it's difficult to study, but what turned out is that, and thanks to all the formulas that I said before, now all the invariants, you can just push them on this smooth ambient space. Well, this ambient space. But what turns out is that under some mild assumption, let's say, which are satisfied by the surfaces that we had been considering, it turned out that the Hilbert scheme of divisor is smooth because it's isomorphic to a projective space. And we could completely write our fourfold intersection numbers purely in terms of something depending on the surface, on a non-smooth ambient space. It may seem a complicated expression, but it is not, because it's just given by the class of the hyperplane divisor in the projective space. You have a twisted tangent bundle, you have tautological bundles, all stuff that you know how to study on the surface. Using this expression, we computed all the invariants in all the cases that we classified. Of course, I mean, you need to satisfy 1 and 2. Let me say that I've been thinking lately on how one can weaken this. I'm sure that you can weaken too. So you can also ask not just everything to be scheme theoretically supported on the zero section, but I expect that you can also thicken out. What I expect is that you will have to replace this with something more exotic, but probably singular, but still with a virtual fundamental class. And I also expect that you should be able to remove some of these conditions. And this, of course, removing that will mean that instead of having a projective space, you will have that Hilbert scheme of divisors. But if you play a bit with your assumption, you can still have a virtual fundamental class. So in principle, I don't say it will be as easy as this expression, but in principle, you can at least write down an expression. So using this expression, let me really briefly say something about something I call fun fact, maybe just fun for me, but something I cannot give an explanation of is that you see here, you have a very long and complicated expression giving these invariants, but after you compute all of them, you realize that they are the same up to a sign to just the Euler class of the twisted tangent bundle over the Hilbert scheme of points, which is very nice because we have a closed formula for that, just given by Carlson and Kunkov. It would have been nice, I mean, it would be nice to just prove this formula because then you don't need to compute all the intersection numbers before, but I have no idea to prove it. Maybe there's some wall crossing behind. But I have to say that this is very sharp because you may wonder, okay, what if you forget fourfolds here and you just say, oh, is this, which just can be expressed in terms of the surface, is this always the same as this, which again, can just be expressed in terms of the surface, so you forget fourfolds? The answer is no. This equality really recognizes, let me scroll back, when you have such an equality and when the moduli space is compact. And this is really weird. I even have to say, this really helped me to understand when the moduli space was compact because I was so sure of that equality and then as soon as that equality failed, I went to check the moduli space and moduli space were either not compact or not scheme theoretically supported there. But still I cannot find a proper explanation of this phenomenon. So this is something I will be curious to understand. Do you have any questions? Okay, let me use my last.
I wanted to ask about this expression. You have an integral where you're integrating something which is like you have one part of like the previous slide. Yeah. So you're integrating something which depends purely on, like, you have these beta amps and so on. So that's the part that you integrate over the Hilbert scheme. And then you have a part which is just kind of powers of the divisor on the projective space, or like this, the Hilbert beta. Have you, I mean, that's kind of looks like, you had power series in that, and that kind of looks like some sort of cybergrid invariant contribution. Have you tried to evaluate it explicitly?
No, so we thought of that, but we didn't try to relate it to cybergrid invariants. But still kind of weird how that can go, in a sense. I don't know how to explain, because that you would expect that to hold, I don't know, more generally, or to say something even if you still can compute it, but you weaken this. But everything that we tried just failed. So, but still, I think there is some more geometry hidden there. So I would be really interested in discussing this more and understanding which kind of other approaches one can use.
But S is here any del Pezzo, right? It's not like something elliptic.
No, here, I mean, the checks that we perform are just for del Pezzo. But as I was saying, I think that you can relax that a bit. And then in some cases, you can do something more general. Don't take my words as written, because it's just thoughts for now, but I think one should be able to go a little more behind. At worst, you have to see something equivalently, but there should be some extension of this.
Thanks.
So if I can still say 5 more minutes, let me explain the other, say, parallel techniques that solve this. The first technique was purely enumerative. As I was saying, you don't really need toric surfaces. It's just nicest to have toric surfaces. And it's really relying on intersection theory on surfaces. This instead is a totally different approach to how to compute invariants. It really uses the toric point of view of this. What do I mean with this? I mean that our X is toric. In fact, there's a C star 2 acting on S because it's a toric surface. And there's a C star 2 acting on the fibers, scaling the fibers. The action that naturally lifts to the moduli space of stable pairs. I won't explain why, but for fourfolds, you have to take the subtorus preserved in Calabi-Yau form. Otherwise, you cannot do anything equivalently. So if you denote by T1, T2, T3, and T4 the coordinates of this rank 4 torus, subtorus preserved in the Calabi-Yau form is the one such that the product of all the coordinates is 1. And the nice feature here is that Thomas proved a virtual localization formula, which has more or less the same shape as Graber-Pandari-Pande virtual localization formula. What does he say? He says that you can perform your invariants as an equivalent integral over the virtual structure induced on the fixed locus, just that you have to invert not the Euler class of the virtual normal bundle, but the square root Euler class. So again, it's another appearing of the square root Euler class. Just to say, this virtual normal bundle is just the movable part of the abstraction theory in K-theory. Let me say that it may seem very easy to write down such an expression, but this square root Euler class equivalently is a nightmare. So trying to compute with this is very difficult, and I'm going to explain why. It's very difficult, but it's very explicit if you're able to find some ways to make it explicit. In our case, how does it work? We have that the fixed locus is 0-dimensional and reduced, so essentially given by a bunch of points. And all of these points, these fixed points, are purely described in terms of solid partitions. This is very nice because solid partitions is something combinatorially. You just forget about the geometry. You can fully translate it into a problem in combinatorics. You can also teach a computer to do it instead of you. The feature here is that, remember at the beginning I said, how do you compute square root Euler classes? In general, the story went like this. You take a maximal isotropic subspace, and up to a sign is just the Euler class of the maximal isotropic subspace. Here, point-wise, the fiber of this class is just a T representation, torus representation. And what is nice is that we can do something weaker than this extracting a maximal isotropic subspace. What it turns out is that always, as a representation, you can write this as a representation V plus its dual. This is very nice and very non-canonical. Of course, you have many choices to do that. I'm going to call this a square root of a representation. It's kind of a halving. And what turns out is that the square root Euler class of the virtual normal bundle is just up to a sign, again, that's where the nightmares come in, of the, is just the Euler class of the this square root of the representation. What is very nice here is then, again, up to a sign, which is different for every fixed point, you can fully compute your invariance just by computing essentially the Euler class of this vertex term, which is an analog of the, it's a fourfold analog of the topological vertex. Let me give an example just to visualize this. How do these fixed points look like? They look like some packing of boxes in 4 dimensions. Of course, I cannot draw in 4 dimensions. And then you have to plug in some extra red boxes that follow some gravity rules. So it's very fun to do it and very explicit. Let me end with giving some pros and cons about vertex formalism, especially compared to the other method that I explained before that was purely relying on intersection theory. The pros is that I spent the whole first part basically on trying to understand whether the moduli space was compact or not, and whether to which kind of fourfolds it was working. But if you forget about compactness and you just work equivariantly, you don't need compactness anymore. So this is great because you can just work for all possible fourfolds as long as they are toric. And again, they work for all toric. You don't have to put extra requirements. For example, just weak-tailed pets or stuff like that. And the other pro is that to compute invariants, usually it's very difficult to compute such invariants. But in this setting, they purely depend on the combinatorics. So you really don't have to do nothing smart from the level of geometry. You just need to sit down and write an algorithm computing it. The cons of this, the drawbacks, are the fact that you saw before the number of, so to every fixed point, you have to attach a sign, a plus or minus. And if you don't know how to do that, well, you know, the number of fixed points grows very fast. And you cannot just brute force them, because then you would have 2 to the number of fixed points, possible choices of signs. And this is very hard. Let me just give an example, some computations that we performed on P3, so local Fano. We performed an example where we had 154 fixed points. And I think that 2 to the 154 points is close to the number of particles in the universe. So of course you cannot brute force this. You have to be smart and you have to figure out some rules on how to give these signs. Luckily we did, so we don't have, I mean, not a theorem, but we have more or less some combinatorial rules on how this sign behaves. Let me also say that in all of this story, I just said how to compute stable pair invariants, so shift theoretic invariants. But I said that all of these checks were checks of the Tau-Malik-Toda conjecture. So of course, in order to check the conjecture, you need also the curve count inside. And all the invariants that we got were either provided by Clement Pandey in their paper or by Bussoberini and Van Garel. So we thank them for sharing them before they were actually online. Let me finish by saying that, let me steal 30 seconds more, just saying that I just described some features of this new theory, but the field is very new, it's a very hot topic, and there's much that you can do. You can do descendant insertion, so you get more conjectures, more wall-crossing behavior. You can do tautological insertion, so that's totally different direction. Or you can do k-theoretic insertion, so my favorite, because they also relate to all the work of Nekrasov and all of its collaborators. Yeah, and so there's much more, and then yeah, I think I stole enough time of your very long day. Okay, so thank you very much.
Thank you, Sergej, for a very nice talk. Any questions?
Ask your question?
Yep.
Okay. Hi, Sergej. Yeah, very nice talk.
Hi.
Okay, yeah, I have another question about your vertex formalisms in the end of your report. So you mentioned that vertex formalism for the fourfold, right? Okay, yeah, around here, yes.
Here.
And my question is that, okay, you mentioned this is available for the toric case and also the non-compact case, but how about for the compact case?
The point is that compact case for fourfolds now it's difficult because we have to get Calabi-Yau. We cannot work outside the Calabi-Yau world. But if you want to use the equivariant theory, then you need some toric structure. But then if you want toric and Calabi-Yau, well, these geometries do not exist, so you cannot have both of them. That's why, in a sense, it's hard to have your variety to be both compact and toric. However, the nice thing that led us in the beginning to provide, that's why in the beginning we were working with the toric surfaces here, and we also classified the compactness of the moduli space, was precisely to have a non-compact but Calabi-Yau toric fourfold, such that the moduli space was compact. And this is nice because then it means that you can still do intersection theory, but equivariantly, because you know as a theorem that all the equivariants will drop in the end. So in a sense, this is the closest possible to using vertex formalism for fourfolds in compact setting. But this is much different from the trifold setting, where you can also prove conjectures using, for example, cobordism arguments, just reducing to compact toric trifolds. Here you cannot do that, so you have to find different techniques. So it's much more limited in a sense.
Okay, thank you very much.
More questions?
Sergej, is there any technique available to study non-toric surfaces?
As I was saying, so I'd say yes, but we have not still written it out. Let me go there. As I was saying, you see here, with this first technique, we kind of just want to rely on the intersection theory of S. We use toric just because we were already working with toric varieties, but you can just drop toric here and still ask, okay, when I realize this as a compact moduli space? And then you can just try to follow this argument. This is independent of being toric, it's just this argument of Choikatz-Klein. You just have to produce some inequalities. These would still hold. And then you just have to figure out how to control this Hilbert scheme of divisors in the surfaces that you get. But what I would expect is that you still get a similar expression. You see, it's not really important toric here. So I expect, but we have not done it, I guess, for laziness, but I guess that you can try to do the same also for non-toric surfaces.
But with the assumption that the sheaves are scheme theoretically supported on S, or?
Yeah, so if you still keep this assumption, then everything should go smoothly, and then I'm sure that you get such an expression. What I was saying before is that I think that you can weaken this and try instead to get this simple stuff. You get, instead of this moduli space, I don't know, you get this other moduli space, and then you can still try to keep track of what's happening to the virtual class. It's more difficult, of course. You won't rely on this expression anymore, but I think something can be said. But of course, we have not explored the situation there yet.
Thank you.
Any more? If not, I think we can wrap it up for the day. Thank you very much. And I'll stop recording now, and I'll see you all tomorrow. Thank you, Sergej.